In this lecture, we'll further deepen our understanding of forces and moments by considering two new concepts: force couples and equivalent systems. The first idea to get to grips with is that of a couple. If two forces are equal in magnitude and have opposite directions, in other words, they have parallel lines of action on a 2D plane, they are said to form a force couple. I ended lecture 1 by asking you to think about an arrangement in which two coplanar forces would not be concurrent. Well, a force couple is one such case. In fact, for two forces on a 2D plane not to be concurrent, they must have parallel lines of action, although they may not necessarily be a couple, which would require them to have equal magnitudes and opposite directions. So, the interesting feature of a force couple is that the resultant force is zero, and yet there is a net moment generated by the pair of forces. In order to calculate the moment generated by a force couple, we simply multiply the magnitude of the force by the perpendicular distance between the two lines of action. Now, as we've seen in lecture 3, a more straightforward way of achieving the exact same thing is to first break each force into its orthogonal components. Then, the horizontal and vertical force couples can be considered individually, with their resultant moments simply added together to obtain the complete moment couple. So remember, if two forces on a 2D plane have equal magnitude and opposite directions, they form a couple, resulting in zero net force. However, the resultant moment is determined by multiplying the magnitude of one of the forces by the perpendicular distance between the lines of action, or, as we've shown here, by considering the couples formed by the orthogonal components of the original force couple. Notice that no matter where we assume the point of rotation to be, the magnitude of the moment generated by the couple, as well as the centre of rotation, will always be the same. Similarly, we can move the position of the couple relative to the point of rotation, but the moment and sense of rotation remain constant. What's important is the position and direction of the forces in the couple relative to each other. The key message here is that the moment generated by a couple is independent of any point of rotation in the plane. Or to put it another way, regardless of where the force couple is positioned relative to the centre of rotation, the moment about that centre of rotation will always be the same. In fact, the moment generated by the couple is the same for all points on the plane. Now we can put into practice everything we've developed over the last 4 lectures. Remember, we said a system of actions can contain forces and moments. We've already seen several examples of this. Our understanding of forces and moments now allow us to replace a system of actions with an alternative but equivalent system of actions. This is a useful technique because it allows us to replace complex systems with equivalent systems that are simpler and easier to analyse. For two systems of actions to be equivalent, they need to satisfy two conditions. The sum of the forces in each system must be equal, and the sum of the moments in each system must be equal. If this is the case, both systems will have the exact same force and moment influence. As always, this is best illustrated with an example. The task is to replace this system of actions with an equivalent system containing only a single force applied at the origin and a directly applied moment. Once that's completed, we need to go one step further and replace that system with a single force without directly applying any moment. The clue here is that we need to use the position of our single force to generate the moment for us. Reflecting on what you've learned so far, attempt to solve this problem yourself first. Let's start off by labelling our original system A and our target system B. So the goal here is to work out the values of m, r and theta that will make system B equivalent to system A. The next housekeeping task is to formally state our sign convention. Make a habit of stating this clearly at the start. Don't be tempted to skip ahead. It's surprising how quickly you can get yourself confused without a clear sign convention to refer back to. First, let's satisfy the equivalent force condition. We know that the horizontal force, Rx, in system B must equal the horizontal force in system A. Therefore, Rx equals 80 newtons. Similarly, the vertical force Ry must equal the sum of the vertical forces in system A. So Ry equals minus 130 newtons. Now, using the geometry of right angle triangles, we can now work out r and theta. So we're halfway there. The next condition that we must satisfy is the equivalent moment condition. So, calculating the equivalent moment in system A and equating it to m, the moment applied in system B yields m equal to 1975 Newton meters. So we can now say that system A is equivalent to system B, in which m equals 1975 newton meters and the equivalent force, or, equals 152.6 newtons, at an angle theta equal to 58.4 degrees measured clockwise from the positive side of the x-axis. Now the next part of the question requires us to replace system A with an equivalent system containing only one force. So we can no longer directly apply the moment m. To avoid confusion, let's call this new equivalent system system C. Let's take advantage of the fact that system A and B are equivalent and work with a simpler system, B. We need to generate a clockwise moment of 1975 newton meters, but without directly applying a moment. So the question becomes, how can we generate this moment using only the force available to us, or, which equals 152.6 newtons? Pause the video here and spend a couple of minutes just thinking about how we might achieve this. The only way to generate this moment is by shifting the force or such that one of its orthogonal components generates the required moment. So, if we shift or to the right along the x-axis, its vertical component, or y, will generate a clockwise moment about point O, exactly what we need. The distance we need to move to the right is simply the lever arm required to generate a moment with a magnitude of 1975 newton meters, so in this case 15.2 meters. Alternatively, we could move or vertically upwards along the y-axis and achieve the same effect with Rx generating the required moment about point O. In this case, because Rx is smaller in magnitude than Ry, we need a larger lever arm to develop the same moment, in this case 24.7 meters. The important thing to appreciate here is that we've satisfied both of the conditions to ensure system C is equivalent to system A that we started with. So the sum of the forces in each system is the same, and the sum of the moments about point O is also the same. This is a crucial thing to understand before moving on. Make sure you fully understand why all systems A, B and C are equivalent. We've covered quite a few topics over the last two lectures, so it's a good idea to have a quick recap now to go back over some of the main concepts and ideas that we introduced. So we discussed what the moment of a force was, and we said the moment of a force was a measure of the degree to which a force wanted to cause rotation about some point of rotation. Now, put in other words, it's a measure of the twisting or rotational effect of a force about a point of rotation. We said the magnitude of the moment of a force was equal to the magnitude of the force multiplied by the lever arm, or the perpendicular distance between the line of action of the force and the point of rotation. Now, a consequence of that is that if the force passes through the point of rotation, the lever arm is zero. If the lever arm is zero, the moment of that force about that point of rotation is also zero. So the main thing is that if a force passes through a point of rotation, it doesn't generate any moment about that point. We have to have some lever arm or some offset in distance between the force and the point of rotation. Now, we said moments could be either positive or negative, and that was all depending on the sense of rotation that that moment would cause, whether that was clockwise or anti-clockwise. Another concept that we introduced in this lecture was that of force couples. Now, if two forces have equal magnitude and opposite direction, which on a 2D plane implies that they're parallel, and they don't share the same line of action. So what that means is they don't lie on top of each other. They're separated by a distance. They're said to form a force couple. Now, in terms of force, those two forces will cancel each other out. So the net force of the two forces within the couple is zero. But there will be a net moment. And the moment generated by that force couple is equal to the magnitude of one of the forces multiplied by the perpendicular distance between the two lines of action. Now, the last idea which we've just introduced was this idea about equivalent systems. Now, the ability to take a system of forces and moments and condense that down into a simpler yet equivalent system is a really powerful idea, and it's going to be something that we're going to be using as we go on through this course.